Okay, take it away.
Okay. Hello, everyone. Good morning, good afternoon. I don't know. My name is Bruno. As Ben has said, I'm here to present my R package named SoundClass. So I'm just going to share my screen. Ben, is it okay? Everyone seeing it?
Looks great.
Okay. So, well, my name is Bruno Silva. This is my fellow colleagues, and I'm going to present now the SoundClass package. I'm going to talk just a little bit about myself to introduce me, and then I'll explain the method used and some of the things that belong to the package. So in reality, I'm an environmental scientist. Afterwards, I did my master's in statistical modeling, and currently I'm a PhD student at Évora University in biology. As Ben has said, I'm interested in the impact of climate change on the interaction between bats and agricultural pests. And I'm using PAM, passive acoustic monitoring, to monitor bat populations and their phenology a long time. So I've started working with bats and acoustic monitoring quite early in 2005, 2006. At that time, we didn't even have some automatic recording devices. All the sampling was done by hand. I had to go to the field with a hand recorder to capture, to record the bats. Then afterwards, automatic recording stations started to be more common. I started to using them. And at that time, I've been doing manual analysis of recordings to identify the bat species. But at a point, I was totally overwhelmed with data, raw data. We had 5, 6, 7 automatic recording stations at the same time, and they recorded everything, not only bats, but birds, insects, background noise, environmental rustling, foliage, many things. So I started to wonder if there were methods more adequate for this type of analysis. At that time, there weren't many automated tools available. And so I started to be very interested in statistics, machine learning. And in 2012, I've applied to a Bat Conservation International grant, which I got, and I started at that time to develop some tools with neural networks, but still with manual feature selection. And then it just started to evolve. Today, technology has allowed many great advances. And afterwards, I applied to the PhD program to continue to develop and hone my skills and knowledge in this topic. So this led to a package, and our package, SoundClass. The accompanying paper was published recently, and there you can see it's kind of a tutorial of using the package. Feel free to download. If you want to contact me for some questions or things, I'm the corresponding author. Please go ahead. So now I'm going to explain a bit about the package and the motivation behind it. So with passive acoustic monitoring being increasingly used to study animal populations, there is a strong need for more tools to classify sound. We need tools for different regions, for different taxonomic groups. And I soon realized that even though the tools were available, especially convolutional neural networks, which I'm going to talk a little bit during this presentation, they are not quite accessible to many people. They are complex to implement, and they require sometimes strong coding and programming background. And so with this in mind, me and my team, we decided to create this package to try to extend the use of these modern techniques to a larger audience, especially to people that don't have the coding skills needed. So in this package, we encapsulate all the steps needed for building a model, training it, and applying it to new data. So this is the workflow of the package. First, as with almost every automatic classification modeling, you need to have a database of known classes, sound events that you know which species or which behavior they refer to, and you have to have a precise location, temporal location in the recording, so that you know where the sound event that you want to work with is. Afterwards, you have to prepare your training data. Depending on the type of model you use, you have a lot of pre-processing to do. You fit the model, and then you have to use it to apply for new recordings. First, we develop graphical user interfaces for every step of the process to ease things a bit more. So this is the user interface for the annotation. Here, you just have to click on the sound event that you want to classify, and then label it. You must know which class, which label each sound event belongs to. You can also add some observations if you want to. This info is stored in a database, a very simple database, where you have the name of the recording, the position, the temporal position of the sound event, the label of the class, and then your observations. Afterwards, you have to prepare your training data. So sound is a very high dimensional and very difficult to work with in its raw format. So you have to convert it to something else. In here, as we are using convolutional neural networks, CNNs, and they classify images. So the first step is to obtain an image of this sound. We opted to use spectrograms. There are other options, but this has given very good results in the past, so we opted for this. To this spectrogram, you overlay the annotations you previously did, and then you work with a small window around the sound event you want to classify. So in here, I'm showing, this is a batch recording, Barbastella Barbastellus, and I'm working with 20 millisecond windows. So this is the training data. This image will be fed to a network, which will then learn to recognize it. Before it enters the network, a denoising algorithm is applied to highlight even more the sound event you want to classify. Then you have to have a network to train. Just a small thing before the network. The spectrogram, when you create the spectrogram, you have to define certain characteristics, certain parameters, Windows length, and overlap, mostly. This is always a trade-off between temporal precision and frequency precision. If you use a larger window, you will have a better frequency precision, but you lose the time precision. So depending on the type of sound you are classifying, you have to tweak a bit the spectrograms until you find the one that fits you. So as you can see, this is the same call with 4 different parameters, and you see that the difference is quite big. For beds, for instance, I would recommend this one or this one here. I think they are the 2 most adequate. So now that you have your training images, you are going to train the model. We provide a bundled model, blank model in the package. It is composed of 3 convolutional layers. This part is the one responsible for obtaining the features, the parameters, the variables that are then fed to the fully connected layers and are classified. So you don't have to manually give nothing to the network. You don't have to measure, for instance, frequencies start frequencies and frequencies of maximum energy, length of the call, nothing. The network will try, obtain parameters, test them, and then updates and refines them. I have here an example to show you. So this is the raw image we saw before. By applying some filters, the image is going to be downsampled, and the features of the image that may be used for classification are obtained. So the image is consequently being downsampled as it passes through each convolutional layer. And this one here, this is the data that it's going to be fed to the neural part for classification. So here we have 2. One is just for obtaining new parameters, and then the softmax layer will output probabilities. For instance, if we are working with a 4-class problem, it will output 4 probabilities that summed will at 1. And the class that has the higher probability is the class the network thinks the sound event belongs to. After we have a trained model, we are going to use it for classification. In the package, we devised this strategy. There are others. We are also working on others that will probably be implemented in future versions. Or as it is, what it does is the recording. This is a new recording that we are going to classify. So we have the trained model, and then we are going to apply it to this recording. First, the algorithm will split this recording into equal size windows. For each window, the trained model is applied, and the class is obtained with a probability. So this is just a test thing so that you can see some things. So in this window, the model didn't found any relevant sounds, so it is discarded. And for instance, in this one here, this is an error, obviously. All these calls belong to the same species. So what the algorithm does, it selects the class with most classifications. In this case, this recording will be classified as a pipistrelle schooling with an 82% probability. It's just the average mean of all the probabilities. So the output of the package is like this. A spectrogram is plotted. Annotation is made where the model inside the window detected the sound event, and the classification is given. So then this information is stored in a database for further use and manual review. In here, we also add one parameter. This is the frequency of maximum energy. At least for bats, this is a very useful parameter that allows you to easily discard errors. For instance, I know that a pipistrelle schoolie doesn't emit at this frequency. It's a bit higher. So I would look at this and see this is an error. So, and then this is for keeping and manual review. And then it outputs a file, Excel file, with the summary of the analysis. It gives you the name of the recording, the class, the probability, Fmax, and the number of calls the model detected. So, right. There are some things, convolutional neural networks are very good at classifying stuff, but they tend to overfit a bit. So it is very important to take some care, especially when you are building your database, your reference database that will be used to train the models. So the size of the dataset is crucial. You should have the most variability possible of your sound events. For instance, the same species may emit different sounds with some variations, and you should have the most you can. Also, you should include background noise, because there are some things that may confuse the network, especially insects and some environmental noises. So it's necessary to have the most sounds you can in your database. The most complete your reference database is, the better your model will be. Also, when you are building the spectrograms, you should use some trial and error to find the optimal parameters. Sometimes this is not done at first. You have to tweak a bit and test a bit. Because, for instance, for a bat, I'm going to tell, bats are, the calls are very short, and the frequency changes very quickly. So a bat call can have 10, 20 milliseconds of length, and the frequency may start at 60 kilohertz and end at 20 kilohertz. So to correctly classify a bat call, you should have a very fine temporal resolution. You should use very small window sizes in the spectrograms. On the other hand, birds that have longer calls, 2, 3, 4, 5 seconds, and the changes in frequency aren't so hardcore. So a bird may start calling at 5 kilohertz and then at 4.5. So in here, you don't need to have such a good temporal resolution, and you can use larger windows. So also the architecture of your network is important. The bundled network has 3 convolutional layers and 2 fully connected layers. For some cases, you may need more convolutional layers to obtain more features, or you should have more classification neurons. It depends. It depends here. It depends a bit, and you should try. Also, there is this particularity that the networks are fitted with a stochastic algorithm, which means that each network is unique. If you train two networks with the same data set and the same initial parameters, you will end up with two different networks. So it's advisable to train 2, 3, 4, 5, and then choose the one that performs better. So this is it. This is the package in a nutshell. And I just would like to say that it was very fun to write and to develop SoundClass. It's very interesting to see a machine starting to learn and be more effective in that learning. It's kind of, I'm a bit of a computer nerd, if you haven't already noticed. And so for me, this is really, really interesting. And so with SoundClass, we try to give to a larger audience the ability to use these complex models that now exist for sound classification. And we try to reduce the number of functions to a minimum and provide graphical interfaces so that you don't have to mess around with the code. Currently, SoundClass is also on-prem, but there is an active development version on GitHub, also with a bug reporting. So feel free to download and try it. Thank you very much for your attention. I hope I was clear enough. I know my English is a bit broken. So thank you. If you have any questions, now I'm available for answering. Ben, I pass the word to you.
That was awesome. Thank you. I really
Thanks.
enjoyed it. And bats are especially hard. I'm impressed to see how well you're doing with them.
Sorry, Rebecca. No, I didn't quite catch the.
Oh, I
That was
just said
low.
I am impressed how well it is doing with bats. They can be really difficult to identify, even just for humans going through the recordings.
Yeah, but well, there is always an error. It's very difficult to reduce from 10–15% errors, but yes, it's performed quite well, especially if the recordings are noise-free. If there isn't many insects in the background or other noises, it performs quite well. Thank you.
Okay, for me to jump in?
I think so.
Thanks. So that's really awesome, Bruno. Thank you so much for sharing this with us. It's a really great tool that you and your collaborators have created. I just wondered about what kind of metrics you include for evaluating model performance, either immediately post-training or when you deploy the model on novel data.
Well, in the package itself, we didn't include any, but I normally use the precision, recall, and the F1 score for evaluating the precision is the amount of recordings from a given class that the model detects. Recall, it's the number of detections that are correct. And the F1 score, it's the weighted mean of these two parameters. It's kind of sensitivity and specificity in logistic regression, you know.
Yeah, awesome. So just to keep going on that, are the kind of metadata that are output from training, are those, do you include in those the things needed to calculate precision and recall or accuracy?
No. You have to use another package.
Okay.
I'm not, yeah, okay.
Thanks.
Caret, the package Caret has a lot of metrics so that you can apply them. Having the list of correct observations and the list outputted by the predictions of the model, you can easily obtain those metrics.
Yeah, okay, great. Thank you.
Hi, Bruno. Thank you very much. Can you hear me?
Yeah, yes, I can.
Okay. First, thank you. I think that is great. I like how the workflow was implemented. I was wondering if it was possible to add like pre-trained networks, like basically incorporate transfer learning in the architecture of the classificator, since it's like quite useful, especially when you you don't have like a big data set of labeling recordings. And also if it's possible like to do something like fine tuning or even doing that augmentation on the fly. So it will be, so it's, so yeah, like basically kind of avoiding like making a new like spectrograms and basically do all the workflow for augmenting the data on the fly.
It's a very interesting question. No, in the package, we didn't implement that ability. If you know a bit about programming, you can, the package uses a foreign, it's TensorFlow and Keras. Do you know? And those packages add the ability to do dot augmentation, to change the training algorithm. We are using the stochastic gradient descent, but the package itself doesn't mess with the training part. It leaves it to Keras. So probably in a later version, we would implement some functions that encapsulate Keras' ability to train the models and to perform other tasks like data augmentation. But right now, with the package, you can do that. You can use the package to do your annotations and prepare some training, and then you can have a generator, a data generator from Keras to increase the data that is shown to the network during training. I hope I answered.
Okay, thank you very much. Yeah. Thank you very much.
Gio?
Yeah, hi Bruno. Thank you so much for the presentation. So you mentioned that a denoising step takes place before the data is used for training. I was just wondering what noise processing you're using there, and also just how much that step improves or otherwise changes classification accuracy as opposed to training on the raw noisy data.
Okay, so the algorithm, it's a spectral mean subtraction per frequency bin. So in each frequency bin of the spectrogram, the mean frequency of that bin, of that frequency is subtracted to each bin. So as I know, it improves classification, not only from bibliography, but also from some testing I've made. I cannot tell you how much it improves, but I think it's a lot. Noisy recordings are very, very difficult to handle. And sometimes even this denoising algorithm doesn't denoise totally the recording, and it may present some problems, yes.
Great, thank you.
So just a quick note: if for more information, you can read the paper. These things are all covered there. Also, there is an example of application with the codes. In the paper, well, as I work mostly with bats, it's the main example, but I also did some models for owl species and for sperm whale clicks. So just to show how the package could be used for several taxonomic groups and environments, underwater, overwater, different frequency ranges. So if you read the paper, some of these questions are answered there. So, thank you.
Diego?
Hi, thank you, Bruno. Thank you for the really nice package. I have a small question. It's probably answering in your paper, but before I read it, perhaps you can answer. If I had to choose one particular stimulus for the network, would you go for a small tonal thing rather than a long complex unit, or what would be your choice?
The small tonal thing seems to work better.
Okay.
Yeah.
Okay. Well, in my case with Starlings, I would need something that recognizes like a clicking pattern, you know, that happens in a kind of
yeah, because the package was mostly developed for bats, and bats have very short clicks, sometimes 2 milliseconds.
Okay.
And it works perfectly well.
Okay, I will play with it. Okay, thank you very much.
Okay, thank you for playing with it.
Bruno, on the slide before this one, you had some links and I didn't have the time to write them down. Do you think you could go back just to the previous slide? Great.
This one.
Yeah. For
And
anyone.
if you want, I can send you the presentation after. I have no...
Cool. So we have one question from Ida about the recommended training data set size.
The bigger, the better. it's the only answer I can provide, I think. Well, it depends on the type of sound event. For instance, if the sound events are very similar across individuals, or if the less variability there is in the sound event to classify, the less database you need to have a good model. So I think this is the best answer. But having computational power available, I would recommend increase the database. Also, as asked before, dot augmentation is a technique used to, with the same data set, you tweak it a bit, you translate it, or you add some noise. So it's real for this type of networks. The database should be big. No, I'll tell you, for one of the models I've been working, I'm classifying European bats. Right now I have around 20 species in the output. My database is composed of 40,000 examples. So it's a lot. But it increases, and there is something that you can do. You don't need to start to train a network from scratch all the time. If you have, for instance, you start by training a network with 10,000 examples, and then you get your hand on another 2,000. You can use those to increment the network that you already have trained. So you don't have to start all over again. So you can start with a small database, being careful to have all the classes that you need to classify. And then with time, you can increment your database and increment the training of your network. So the package allows that. It's going to be the focus of my next paper.
The other thing I would say, just adding on to Bruno's point is, 40,000 is amazing, but that's not the minimum.
No.
And depending on the sound that you're interested in detecting and classifying, maybe you need a few hundred examples from varied contexts. It's not that you need to spend hundreds of hours creating thousands and thousands of annotations.
Yeah. No, yeah, thanks, Ben. Thanks for adding that. Yeah, because for some things you don't need such a large database, it's true.
We've got a question about are there any minimum requirements for using this with regards to like hardware requirements for RAM or GPU?
I would recommend at least 8, 16 gigabytes of RAM, and at least an i5, i7, 6 cores. I don't use GPUs for training. I only train on CPU. So, but yeah, I use an i7 with 6 cores and 16 gigabytes of RAM, and it's performing quite well.
Well, that's really great. Thank you for all these questions. And I definitely want to explore this package more and use it not on bats, for something else. But so we have about 20 minutes left. And I was thinking that, one thing that I think would be really great, like we have people from all around the world here from different backgrounds in bioacoustics. And, with this presentation series, we're learning about interesting tools and studies, but we're not learning about each other. And so I think this topic of machine learning is something that, each of us is potentially interested in and has explored. And so I'm thinking it would be a great time to do breakout rooms, which I think would be a first for this session. For this series. And in these breakout rooms, even if we're just meeting each other, that would be good. But if we want to talk about what our experience or interest is with machine learning and potentially resources that we found helpful, I think that could be really nice. So I'm going to create 9 or 7 breakout rooms. So they'll have 7 to 8 people per room. And yeah, let's see what happens. Why don't we meet for about 15 minutes? And looking forward to it. So I'm going to create these now. And if you want to ditch out, then feel free. But if you want to stick around, we'll do that here.